Good morning. Let's start with the contour integration assignment 8. There is a remark. Let's see with the contour consisting of the real axis from minus r to r followed by a semicircle in the upper half plane from r to minus r, and this semicircle is tau. If you look at the figure, the real axes are from minus r to plus r followed by this semicircle tau in this upper half plane from r to this minus r. If suppose I have to consider the function fz equal to 1 over z to the power 2n plus 1, where n is belonging to the natural numbers. Now if such kind of function appears, then this power of z can be very, very large as n is belonging to the natural number. So for this, we need another way to find the poles. First, the poles of the fz are given by, of course, we have to take denominator equal to 0. And then this z to the power 2n is equal to minus 1. Let me write this because the power can be very, very large. So I should write it in the powers of the exponent, right? This power can be very, very large. So in the form of exponent, I can write here in place of minus 1 as e raised to the power 2k plus 1 pi iota. Right? And this z is equal to then become e raised to the power 2k plus 1 pi iota over 2n, where this k is belonging to the set of integers. So therefore the poles of fz are at the points, put k equal to 0 first, you will get e raised to the power pi iota over 2n. Then put k is equal to 1. You have to take k to be as the set of integers as 0, 1, the positive integers up to 2n minus 1. Then you put k is equal to 2, you will get e raised to the power 5 pi iota over 2n. Likewise, you get so many poles over here. Now the point is, which poles lie inside the circle C? So half of these poles lie inside the circle C, and half of remaining last half of these poles lie outside the circle. So first half of these poles lies inside the circle. Suppose you are getting 6 poles, then first 3 poles will lie inside the circle, right? So out of these 2 n poles, first n poles lie inside C and the last n poles lie outside the C. And then according to that, you find the residues of fz at those poles which are inside the circle, and then you have to apply the Cauchy residue theorem to get the required result. So let's move on to the example. Prove that the integration 1 over x to the power 4 plus a to the power 4 dx, the integration is from 0 to infinity, is equal to root 2 pi over 4a cube. So we will integrate fz equal to 1 over z to the power 4 plus a4 along C, where C is the contour. This is your contour from this real axis minus r to plus r, followed by the semicircle tau from plus r to minus r. This is your C, right? You have to always write this in every solution. Now the poles of the fz are given by, of course, putting the denominator equal to 0, you will get, let me change the color of the pen. Thank you. So this is z to the power 4 plus a to the power 4 equal to 0. Then z to the power 4 equal to minus a to the power 4. This is equal to minus, okay, instead of minus 1 in the remark, which I place in the remark, this instead of minus 1 write e raised to the power 2k plus 1 pi iota. So a the power 4 as it is, instead of minus 1 I'm writing e raised to the power 2k plus 1 pi iota. So this implies z is equal to now a the power 4 e raised to the power 2k plus 1 pi iota over 4. Very fine. So now your k is starting from 0, 1, 2, 3. As the power is 4, so number of the integers should be 4 only. Putting this, the value of k one by one and get your poles now. So the fz has simple poles at the points. Putting k equal to 0, you get a e the power pi iota by 4. Then putting k equal to 1, you get a e the power 3 pi iota by 4. And then a e the power 5 pi iota by 4. And then a e the power 7 pi iota by 4. Now out of these 4 poles, the first 2 poles lies inside the C, right? So we have to calculate the residue of the function at these 2 poles only. So let alpha denotes any one of these poles. Suppose, now what is your function? Your function is this 1 over z the power 4 plus a4. Now if alpha denotes any one of these poles, so I have to put here this alpha the power 4 plus a the power 4 equal to 0. This is what it means. That means alpha the power 4 is minus a the power 4, right? So if alpha denotes one of these poles, then alpha the power 4 is equal to minus a the power 4. So therefore residue of the function at alpha is equal to, the formula is limit z tends to alpha, z minus alpha into f of z, which is equal to limit z tends to alpha, z minus alpha, and function is z the power 4 plus a the power 4. Right, now if you take the limit, now this is if you put here alpha, this is 0 by 0 form, right? And we have to use the L'Hopital's rules over here. So that is equal to limit z tends to alpha. This is because it is 0 by 0 form, you derivate the numerator, that will be 1, and then we take the differentiation for the for this denominator, this will be 4z cube. And now it's very simply to put the value of alpha over here. This is 1 over 4z the power, alpha the power 3. Now because I need alpha the power 4 in my expression, I know that this alpha the power 4 is minus a the power 4. So I must make this alpha the power 4 finally. I'm having alpha cube over here. To make alpha the power 4, I must multiply and divide by alpha. So I get alpha over 4 alpha the power 4. And this is equal to alpha over 4 a the power 4 with negative sign, because alpha the power 4 is equal to minus a the power 4, putting the value of alpha, that is minus a the power 4. So now you find the residue of fz at the 2 poles which are lying inside the circle, which are this first one and the second one, by just simply putting the value. Now instead of having, this is in black color pen, I mentioned, instead of having all these steps that you apply first the formula and then taking the L'Hopital's rule and then putting z equal to alpha, instead of doing all these things, to avoid all these things, there is a little remark over here. Suppose your function is 1 over z the power 4 plus a the power 4, and you have to calculate the residue of fz at alpha. You just have to do this. Put this equal to 1 over just take the derivative of this denominator only, which is 1 over 4z cube at z equal to alpha. So this is 1 over 4 alpha cube, and then you multiply, divide by alpha to get your required alpha to the power 4. So this is the easiest way. Instead of taking L'Hopital's rule again and again in every solution, you just have to write the residue of fz at alpha as the function that's 1 over, and take the denominator, the derivative of this denominator. That's it, right? So you just have to derivate the denominator with respect to z. Now the residue of fz at this ae the power pi iota by 4 is, just put the value of this, because alpha is denoting one of these poles. So just put the value of this in alpha. So this is minus ae raised to the power pi iota by 4 over 4a raised to the power 4, and we'll get minus e raised to the power pi iota by 4 over 4a cube. Similarly, the residue of fz at this pole is, putting this in alpha, you get minus a e raised to the power 3 pi iota by 4 over 4a raised to the power 4. It cancelled out. So this is equal to minus e raised to the power 3 pi iota over 4 over 4a cube. Right? So we got the residue for these two poles, and now we apply, before applying the Cauchy residue theorem, let's solve the sum of the residue here only. So their sum is equal to minus 1 over 4a cube taking common. So it is e raised to the power pi iota by 4 plus e raised to the power 3 pi iota by 4. This is equal to minus 1 by 4a cube, e raised to the power pi iota by 4 minus e raised to the power, can I write it as minus pi iota by 4? Let me explain you. Now e raised to the power 3 pi iota by 4. What is this actually? If you remember the Euler's formula, this is cos of 3 pi by 4 plus iota sine of 3 pi by 4, right? So this is equal to cos of, can I write 3 pi by 4 as pi minus pi by 4 plus iota sine of, again this is pi minus pi by 4. And what is cos 180 minus theta? It is minus cos of pi by 4 minus, this is plus iota sine. What is sine of 180 minus theta? It is simply sine of pi by 4. Now taking the negative common, and I get cos pi by 4 minus iota sine pi by 4. Putting this back in exponent, this is e raised to the power minus iota pi by 4. So that's why I write e raised to the power 3 pi iota by 4 as minus e raised to the power minus pi iota by 4. This is the explanation. So this is equal to minus 1 over 4a cube. This is, if you open this, this will be 2 iota sine of pi by 4. Just open this. Something will be cancelled out, and remaining these two, this will remain, which is minus root 2 iota over 4a cube. Very fine. Now by Cauchy residue theorem, we get this integration is equal to 2 pi iota times the sum of the residues, and sum of the residues we have just solved here, which is minus of root 2 iota over 4a cube. And this is equal to, I know that iota is iota square, which is minus 1. So this will be again positive. 2 as cancelled with this 4. And this is equal to root 2 pi over 2a cube. And now I have to split this contour in real axis and along the semicircle tau. I know that this contour is equal to, whenever I should take the real axis, I must write the variable in x, and if I take the semicircle tau, I must write the function in z variable, right? This is very, very important. Now from 1 and 2, just put the value over here. This whole sum is equal to this integration over c, and this just we have found out that this integration is root 2 pi over 2a cube. So I'm writing this sum to be equal to root 2 pi over 2a cube. And now I have to calculate this part. This part always comes out to be 0. And the formula, okay, on calculating this part, I must take the r tending to infinity. This is a required formula, that limit r tends to infinity on this semicircle tau 1 over z the power 4 plus a the power 4 dz is equal to iota pi minus 0 limit z tends to infinity z into f of z. So this is equal to iota pi limit z tends to infinity z. What is the function? It is z the power 4 plus a the power 4. If you take z the power 4 common, so you will get pi iota limit z tends to infinity. This is 1 over z cube over 1 plus a the power 4 over z the power 4. And when you put z tends to infinity, this will be 0. Putting this value over here, so the second term will be 0, but you have to let r tends to infinity in this whole equation 3. So letting r tends to infinity in 3, now whenever I put r tends to infinity, here this minus r to plus r will change into minus infinity to plus infinity. So this is minus infinity to plus infinity, and the tau term is getting 0. So finally this is equal to root 2 pi over 2a cube. Very fine. Now I need the integration from 0 to infinity according to the given question. Because I know that this function is even function, right? As 1 over x the power 4 plus a4 is an even function. I know the result for this even function whenever I'm having this as even function. So I can put the limit at 0 to infinity twice. So this is x the power 4, a the power 4 dx is equal to root 2 pi over 2a cube. And this is 0 to infinity 1 over x the power 4 plus a the power 4 dx is equal to root 2 pi over 4a cube, the required result. I hope it's very clear to you. So let's move on to the next example. Evaluate the integration from 0 to infinity x square over x the power 6 plus 1 dx. Again we have to integrate fz equal to z square over z the power 6 plus 1 along c first. And c is the contour from real axis from minus r to r, followed by this semicircle tau in the upper half plane from plus r to minus r. This thing is very, very important to mention which contour you are considering. Now the poles of fz are given by, of course, take your denominator equal to 0. So z the power 6 plus 1 is equal to 0, which implies z the power 6 is equal to minus 1. Again, I have to write instead of minus 1 as e raised to the power 2k plus 1 pi iota. Very fine. Where k is belonging to integers, and then this implies z is equal to e raised to the power 2k plus 1 pi iota over this 6. So from where k starts 0, we have to take the positive integers 3, 4, 5. Okay, so number of this integer 6. So for this 6 integers, put the value 1 by 1, you get 6 poles, of which first 3 lies inside the circle, inside your contour C. So thus fz has simple poles at the point. Putting the values first, put k equal to 0, you get e raised to the power pi iota over 6. Then putting k equal to 1 over here, I get this as e raised to the power pi iota over 3 pi iota over 6. And then e raised to the power 5 pi iota over 6, e raised to the power 7 pi iota over 6, e raised to the power 9 pi iota over 6, and last e raised to the power 11 pi iota over 6, of which only this first 3 lies inside the C. So I have to calculate the residue for only these 3 poles. Let alpha denotes one of these poles. Then what is our function? This is our function. Now alpha is denoting one of these poles. That means here in the denominator part, put alpha the power 6 plus 1 is equal to 0. That is alpha the power 6 equal to minus 1. So if alpha denotes one of these poles, then the condition is alpha the power 6 equal to minus 1. Now the residue of fz at alpha is equal to what I have told you. We just have to derivate the denominator part, right? First, what is the function I'm having? Here, put alpha square and the derivative of this denominator, which is 6 z the power 5. Put alpha over here then. Okay, I will write this. Numerator as it is, over derivative of the denominator is 6 z the power 5 at z equal to alpha. Now is it fine? Okay. Putting alpha over here. So this is, the residue is alpha square over 6 alpha 5. Now because I need alpha the power 6, right? For my condition here, I need alpha the power 6. So I have to multiply and divide with alpha. So this is alpha cube over 6 alpha the power 6. And alpha the power 6 is negative 1. So this is equal to minus alpha cube over 6. Now the sum of the residues of fz at these poles, minus 1 over 6. Now just put the value of your poles over here, alpha. Now what is your first pole? And my first pole is e raised to the power pi iota over 6, I guess, right? So I have taken minus 1 by 6 outside, and instead of alpha write here e raised to the power pi iota over 6 with cube. Then the second pole is e raised to the power 3 pi iota over 6 with cube. And the third one is e raised to the power 5 pi iota over 6 with this cube. So this is minus 1 by 6. This is e raised to the power pi iota over 2. This is e raised to the power 9 pi iota over 6. Plus this is e raised to the power 15 pi iota over 6. Now this is equal to minus 1 over 6. E raised to the power pi iota by 2 is negative, e raised to the power pi iota is negative 1. E raised to the power pi iota by 2 is iota. E raised to the power 2 pi iota is 1. I know that these are equal to these values. So putting e raised to the power pi iota by 2 as iota, you can also apply the Euler's formula over here to get this value, that is cos of pi by 2 plus iota sine of pi by 2. That is iota. So this is iota. You know that e raised to the power iota theta is cos theta plus iota sine theta. If you do not remember this formula, you can apply simply this Euler's formula and solve your value for e raised to the power pi iota by 2. If you look, this is cos pi by 2 plus iota sine pi by 2. So cos pi by 2 is 0, you get plus iota. Sine pi by 2 is 1. Or you can learn these formulas, okay. Let's move on. Plus, can I write e raised to the power 9 pi iota as 6 pi plus 3 pi iota by 6? Doesn't matter. Plus, instead of 15 pi, I write 12 pi plus 3 pi iota over 6. Very fine. Minus 1 by 6 iota plus. Now separating this, e raised to the power 6 pi over 6. This will be pi. So this is pi iota. And this is e raised to the power 3 pi iota by 6. This will be pi iota by 2. It's very simpler now. Plus, so this will be e raised to the power 2 pi iota. And this is e raised to the power pi iota by 2. Now you can very easily put these values over here. And I get this to be equal to minus 1 by 6 iota. Second term will be minus iota. Third term will be plus iota. So this is equal to finally minus iota over 6. So by Cauchy residue theorem, we get this integration is equal to 2 pi iota times the sum of the residues, and sum of the residues we have calculated just now. This is minus iota over 6. So iota is iota square. The sign will be positive now. So this is pi by 3. Splitting this contour in real axis and the semicircle, which is equal to then pi by 3. We have to calculate this. The formula for this is limit r tends to infinity, integral over tau z square over z to the power 6 plus 1 dz. We can only apply this formula if I write limit r tends to infinity. Very important. So this is equal to iota pi minus 0. That is iota pi limit z tends to infinity, z into the function is, I guess, z square over, let me check, z square over z to the power 6 plus 1. So this is z cube, taking z to the power 6 common, and you will get limit z tends to infinity 1 over z cube over 1 plus 1 over z to the power 6, putting z tends to infinity, so I get 0 simply. It always comes out to be 0. Put this value over here in the equation 1, and also when you put this value before that, you have to hold this equation 1 to be letting r tends to infinity first. So letting r tends to infinity in 1, this will change to minus r plus r will change to minus infinity to plus infinity, and then the second term will be 0, and you get this is equal to pi by 3. You can't put the value of this term without taking limit r tends to infinity in 1. First you have to take r tends to infinity and then only you can put the value, because this result is for limit r tends to infinity. You have to mention. So because this function is again even function, so this is 0 to infinity twice x square over x to the power 6 plus 1 dx is equal to pi by 3. And finally this is 0 to infinity x square over x to the power 6 plus 1 dx is equal to pi over 2 goes this side 6. Hence the result. So these are very nice and good questions, and also the expected ones. Thank you very much. We meet in the next video. Goodbye. Have a very nice and blessed day. God bless.